I'm going to begin. Hey everyone, welcome back to multimodal machine learning. Today I'm going to talk more about reinforcement learning and really wrap up some of the ideas in generative models that we've talked about last Thursday. So if you recall, last Thursday we started with these deep generative models. We've talked about their applications in image generation, and we left out this part of applying them to text generation. So today we're going to wrap up reinforcement learning and then also link back to how we can do generation of text, which are these discrete tokens. And we're going to use some ideas from reinforcement learning to actually help us do text generation. So just some admin stuff first. The instructions for the midterm reports and also midterm presentations are on Piazza. So recall that you first have to do a pre-recorded presentation, and that's due on Friday, November 13th. That's in about 2 weeks. And you also have to write up a midterm report, and that's also due in 2 weeks on about November 15th. So just make sure you start working on both of these midterm assignments right now and not leave it until the last minute. The whole goal of the midterm report is to implement some of these multimodal baselines for your problems and really do some error analysis of these multimodal baselines and really go more in depth into your proposed ideas. Also, LP made this post about there being wildcards for readings as well. So we've already announced that there are wildcards for your project assignments. So those are free 24-hour extensions for either your proposal, midterm, or final reports. And we're also introducing it for your reading assignments. So I think each student gets one wildcard that can extend one of the reading assignments by up to 24 hours. So make sure you check out details on Piazza. And also recall that, whenever we're giving lectures, just feel free to type up your questions either on the chat here. I'll be looking at it live, and also type up questions on Piazza. And other TAs will be following up on Piazza about these questions. So let's begin. For today's lecture, again, some acknowledgements from the Deep RL courses at Berkeley and CMU. Again, I'm going to go through at a really high level this introduction to reinforcement learning and really focus on the multimodal applications. But if you really want to go more in depth, I would encourage you to check out these semester-long courses at other universities. So just a quick recap. Last week, we kind of looked at the reinforcement learning problem. We looked at an agent who is situated in some environment, and this agent continuously starts in some state and take actions and observe rewards and go to next states within this environment. So this sequence of state, action, and rewards is known as its trajectory. We also looked at this formalism of reinforcement learning, being that there being a set of states S in which the agent could be in, a set of actions A, which an agent will start sampling actions from, as well as a transition function, which tells you, given a particular state and a particular action, what is the distribution of next states that the agent could end up in. And also this reward function. So given a particular state and taking an action and going into a particular next state, what is the reward returned by the environment? The agent is in some start state at the beginning. And the goal of reinforcement learning is to maximize these cumulative discounted rewards across a really long-term period, across a horizon H. And we've seen how this Markov decision process of an agent being in some environment really encapsulates many of the broad applications of real-world reinforcement learning. So that includes a robot being an agent situated in some environment in which it has to explore, and also in multi-agent reinforcement learning settings where there's multiple agents, in this case, 22 players playing soccer, situated in some environment and trying to maximize rewards of scoring a goal. So this general reinforcement learning and these Markov decision processes are really broad ways of encapsulating these tasks. All right. So we looked at in reinforcement learning, the goal is to maximize this cumulative long-term reward. So at a particular time step, we denote that as G of t. And what that's equal to is, the reward at the next time step, that's your immediate reward, as well as rewards into the future. And we've seen that we want to discount these rewards into the future by a factor gamma, which is called a discount factor. And the goal of this discount factor gamma is to make sure that both empirically and theoretically, you can actually build policies and converge. And it's also borrowed from this idea in economics that, money you have now is more valuable than money that you might have in the future. So the goal is to maximize this set of long-term total discounted rewards. And that's where the main difference from supervised learning is, right? In supervised learning, you just care about an immediate reward, but in reinforcement learning, you care about this long-term discounted rewards. And again, just to recap, a discount factor close to 0, which means that all the rewards in the future are discounted to be 0, and you care more about rewards in the immediate short term. And on the other hand, this large values of the discount factor gamma close to 1 means that you care more about long-term rewards, possibly at the expense of short-term rewards. And the whole goal of reinforcement learning is to learn a policy. And a policy describes a distribution over actions given a particular state, pi of A given S, which basically tells you, for all states that the agent could possibly be in, what is the distribution of actions that I should take in order to maximize my long-term cumulative reward. So here's the slide that summarizes everything. An agent in some environment, the important terms in the MDP, the goal of reinforcement learning, which is to find the best policy, take an argmax over all policies that maximizes the expected long-term reward following action under this policy. And we also looked on Tuesday, the main differences between reinforcement learning and supervised learning. The fact that reinforcement learning involves making sequential decisions, which allows you to look at cumulative rewards, while supervised learning only looks at one-step decisions and maximizing immediate reward. In reinforcement learning, we also run into this issue of sparse rewards. So that means taking multiple actions across a very long horizon, only observing very sparse rewards at the end. But you don't get that in supervised learning, because in supervised learning, for every prediction that you take, you have a dense reward. And sometimes in reinforcement learning, the environment may be unknown. So in case of Markov decision processes, not knowing the transition probabilities, but in supervised learning, the environment, which is your set of predictions, are always known. So just to quickly recap last week, on Tuesday, we looked at the first case where if we had a fully known Markov decision processes, where we could enumerate all states, we knew the transitions, and we knew the rewards, we derived this set of Bellman optimality and Bellman expectation equations. Essentially, these are equations regarding Q star or Q pi. So what Q star would mean is given a particular state and taking a particular action, under the optimal policy, what is my expected long-term reward? And for V star, so that will be given a state, and for taking the optimal policy, what is the long-term expected reward starting from that state? So these are the values of the Markov decision process that you want to calculate. And we show that we could derive using equations these exact optimality equations of relating your Q stars for a particular state and action with your Q stars for other states and other actions into the future. And we could therefore optimize our Q stars in order to respect this optimality equation. If you're working with your optimality equations, it's called Q value iteration and value iteration. If you're working with expectation equations, that means computing Q of pi or V of pi of a specific policy, that'll be called Q policy or policy iteration. So we show that at least in these simple cases where you could fully enumerate these states, compute this expectation with respect to your transitions exactly, you're guaranteed to converge to the optimal policy. But in the real world, you don't actually have these assumptions. This only works for small and discrete state and action spaces. So it doesn't really work for high-dimensional states being images and actions being continuous. And likewise, it requires known transitions in the Markov decision process, which you don't get in the real world. So to relax that assumption, we looked at MDPs with unknown transitions. So we went from Bellman optimality equations to actually replacing these true expectations over your next states with just approximate expectation. In other words, samples of next states. So in other words, when you're in a state and a particular action, you would just, give that to the environment and see what the environment returns you as its next state without knowing the exact transitions. And we saw here that this idea of exploring the environment is important to use an epsilon greedy method. So in other words, leave epsilon probability of you exploring in the environment randomly instead of depending completely on your current policy, because your current policies are not good. And again, once you replace this expectation by samples, you would like to solve for your Q stars that respect this Bellman optimality equation. And what you would do is that you would treat the right-hand side as a target and the left-hand side as the old estimate, compute the difference, and you want to minimize this difference to 0. Again, the issues are that you will have to keep all your Qs of S and A separately. So in other words, you will keep a table that has number of S rows and number of actions columns. So it still requires small and discrete state and action spaces, although now you do not need to use the true transition probabilities to compute the expectation, but rather using samples. So the next question is, how can we generalize this to even work with unseen states and large and continuous state and action spaces? So that's when we extended tabular Q-learning to deep Q-learning, which is the idea that instead of keeping a table of your Qs across all states and actions, I would like to amortize it, but just learning a single weight function, a set of neural network parameters in practice that takes in a state and predicts your QSAs for all possible actions. So the benefit here is that just because you have really powerful function approximators, if you've trained your model for a particular state to predict its QSAs for a very similar state, you can also apply it through your function approximation and get similar realistic values of your QSAs. So now it works for unseen states. And by good choice of your function approximation, be it convolutional networks or recurrent models and transformers, you can also work with high-dimensional state spaces such as images and text. But the ideas, the optimization has the same ideas, which is to treat the right-hand side as a target and the left-hand side as the previous estimate. We know that at optimality, these Q stars on the left and right-hand side should be equal. So what you can do is take the difference and try to minimize that to 0 using gradient descent. We saw that this naive method might have some issues with correlated samples and non-stationary targets. And we also looked at how we can alleviate some of these issues by using these replay buffers, experience replay buffers, and sampling a mini batch of transitions that are not correlated with each other. And to remove the problem of non-stationary targets, you will keep one set of weights fixed. So at least your targets that you're trying to match are fixed, and you're only updating the weights as given by your predictions, and only replace these previous weights W minus with your latest set of weights every 1,000 iterations. So all of these were done on Tuesday. So this is just a very quick recap of what we've done. And using these ideas of gradient descent plus exploration, epsilon greedy exploration plus experience replay and fixed Q targets, this actually works for high-dimensional state and action spaces and also generalizes to unseen states. And we've seen how this can work for these games, including like Atari games, where we have these images as states. So recall, all we've done so far, we've looked at three methods of basically estimating our Q stars, right? We started with these policy and value iteration to solve them exactly. We've looked at Q learning to solve them approximately, and deep Q learning, which further involves deep networks. All of this was to find your Q stars, which is the action value function for a particular state and action. So if we have these Q stars, we know that we can obtain the optimal policies using epsilon greedy. So if the action satisfies the argmax over all actions, then you would take that with really high probability, and otherwise you would take maybe very small, small probability of random actions. And likewise, the other method was to solve for your V star, right? So V star would be a value iteration. And likewise, we can relate our Q stars and V stars. And again, if we solve for V star, what we can do is we can also obtain the optimal policy, but now you have to do one step look ahead. So in other words, given a state, I'm going to take a max over possible actions. And for each action, I'm going to compute an expectation over possible next states, the reward that you obtain, and the optimal value function for the next state. So that allows us to compute the utility of each action, and the action that satisfies the argmax would be the action that's taken by the optimal policy. So all of the methods we've talked about on Tuesday would find these Q stars and V stars as an intermediate step before we actually obtain the optimal policies, which is the one that we care about. So in today's lectures, we're actually going to give an alternative perspective on reinforcement learning. Instead of optimizing for our value functions, our Q stars and V stars, and then inferring the policy, we're going to try to optimize for the policy directly. So we're going to forget all these Q stars and V stars. We're going to forget MDPs, and we're just going to optimize for this policy directly. And we're going to see whether we can derive some good algorithms for that. And afterwards, we're going to look at this set of algorithms called actor critic methods, which kind of combine Tuesday's lectures and today's lecture. And then we're going to look at some applications. So again, on Tuesday, we look at all these state value functions and action value functions, your V's and Q's. And after we obtain these optimal V's and Q's, we then derive the policy. Now, this is in general called value-based RL, named for the fact that we are trying to derive these optimal state and action value functions. And the other perspective of RL is called a policy-based RL. So in other words, we're going to forget these value functions, our Q's and V's, completely, and instead just directly learn a policy. So what would that look like? So a policy would take in a state and it would try to output some set of actions. In other words, given state, it will try to output a distribution over all actions that you can take. And in general, we're going to assume that we have a set of parameterized policies that are given a state, in this case, an image, go through a bunch of neural network parameters data and outputs a distribution over your actions. So in this case, you just have this paddle moving up and down. So you will just have one output neuron that represents the probability of moving up, and 1 minus the value of that neuron would be the probability of moving down. So you see, in this case, you have nothing about Q's and V's, and you're just directly parameterizing a policy from states to actions through a set of parameters data. So why do we want to do this? So there's a couple of reasons. One reason is that often your policy pi can be simpler than Q's and V's. So consider the case of training a robot arm to kind of pick up some objects, right? So if you want to really define a Markov decision process for a robot arm picking up these objects, you possibly have to define all your state as all possible parameters in the robot hand. So all possible parameters across all possible joints that a robot hand contains. So your QSAs and your V of S could be very high dimensional. But your policy, instead, it could abstract across all of these very low dimensional states, very fine grained states, and just define some high level semantic policies, such as open or close your hand. So you could possibly train a model that just has two output neurons, one, the probability of opening a hand, and two, the probability of closing a hand. So this is an example of your policy being simpler than the Q's and V's across your Markov decision process. Another issue is that, for both your V's and Q's, once you compute them, you have to do one more step before you actually derive your optimal policy. So this works, we saw that for V stars, you guys do one step look ahead. And sometimes this one step look ahead is hard if you have a very large number of possible next states that you could transition to. Sometimes computing this expectation might be difficult. And likewise, even if computing this one step look ahead is not difficult, you do need an argmax over your actions before you can get the best possible policy. And that presents a challenge for continuous and high dimensional action spaces. You might not be able to do this argmax over your actions very easily. So sometimes it makes more sense to directly optimize for a policy instead of computing these Q stars and V stars before obtaining a policy. So that is the main motivation of today's lectures. On Tuesday, we looked at value-based methods. Today, we're going to go into policy-based methods, which directly learns a policy. And then at the end of the lecture, we're also going to look at this set of methods called actor critic, which really combines the best of both worlds. So obviously, since there's two branches of methods in RL, value-based and policy-based, there must be some trade-offs, right? So there's some both conceptual and empirical trade-offs. Conceptually, policy-based methods, directly learning the policy, you would optimize what you care about. On the other hand, for value-based methods, you're indirectly solving the problem because you're first solving your Markov decision process, which is good because it exploits the problem structure. But in some sense, you're indirectly solving for the optimal policy. Empirically, policy-based methods are in practice more compatible with your deep networks. They are more versatile and they're more flexible. And we're also going to see how we can kind of extend these policy-based methods even beyond reinforcement learning to text generation. On the other hand, value-based methods, they're more compatible with exploration, so defining things like epsilon greedy exploration and off-policy learning, and in particular because they exploit the problem structure of these Markov decision processes. They are more sample efficient when they work. So a bunch of trade-offs between policy-based and value-based methods. So now let's go into detail. How exactly do these policy-based methods work? So we're going to look at this very simple game. This is the pawn game where this is the opponent and you're controlling this single paddle. It's just two actions, move up and move down. And the goal is to bounce the ball into the opponent's area while preventing the opponent from bouncing their ball into the same ball into your area. This is a very simple pawn game. And we're going to see how we can design a policy-based method to solve this. So you've seen that this game operates on raw pixels. We have this pixel which depicts the score of yourself and the opponent. We have the paddles for yourself and the opponent, the positions, and also the ball. Right. So in this case, it's an 80 by 80 height by width image. So we're going to define a model. It can be a neural network or a convolutional model with some hidden layers with of parameters theta that predicts the probability of moving up. Again, since there's just two actions, you can just define one neuron, the probability of moving up, and conversely, you have the probability of moving down, which is 1 minus that action. And we know that in this game, if you successfully bounce your ball over, you get a reward of +1. And otherwise, if the ball gets bounced by the opponent across your side, then you get a score of -1. And then the goal is, how can we actually learn this set of parameters theta that prescribes a good sequence of actions to actually allow us to consistently score points. So now suppose for simplicity that we had these training labels. So in other words, given all these states x1, x2, x3, we knew what we should do. So in other words, we could maybe get a human to play this game, a human expert, and for all these states, it will give you the perfect sequence of actions to get this reward. Then you would probably treat this learning problem as a supervised learning problem. So you're given some inputs, and you're given these targets, whether you should move up and down, as given by a human expert. And what you would try to do is to maximize the log probability of the correct action given your state. So this is simply your cross entropy loss. And you would do an average over your sample, your data points. That would be your objective function, and you will kind of solve that using gradient-based methods. That's if you knew the training labels for every state. But of course, the main issue here is that we don't have labels. We don't want, or we don't have a human expert labeling it for us. So the question is, should we actually go up and down? What should these training labels be? So let's just try and act according to our current policy. So this model defines a policy, which is a probability of up and down given state. So just given this policy, I'm gonna follow it. So maybe at the initial state, it outputs a higher probability of moving up, and then after sampling from it, you actually move up. And that gives you into a new state. And given this new state, I'm gonna put it back into the current model. And the model describes a current policy that maybe tells me to move up. And then you probably move up again, and then move down, move up across your sequence of states as prescribed by your current policy. If you recall, this sequence of state and actions as defined by your current policy is called a trajectory. So after a long term of playing, obviously we have this sparse reward problem in reinforcement learning. So we don't get reward signals every time step. But across a sequence, maybe we finally observe some reward. So maybe, after the sequence of 6 steps, you are able to bounce the ball over to your opponent's side and you win. So you get a +1 reward. And I'm just going to keep doing this. So, for certain start states, I'm going to use my current policy. I'm going to win at the end. Maybe for a certain, and then I'm going to reset my start state. I'm going to follow the policy again. And, it ends quicker because I lost. And maybe for another one I lost, and for the 4th one I won. So I can collect many of these rollouts given my current policy. So using these rollouts, what can I do? So we know that in this sequence of actions, we don't exactly know what we did well, but we know that apparently it was something good because we got a positive reward. And likewise for this one. And on the other hand, for this sequence of actions that we've been taking given our policy from the initial start states, we don't know what we did, but we know that it was bad because we lost. So what we're going to do is just to pretend that every action, we're going to give equal credit to each of these actions that we've taken across this trajectory where we've won. And for each of these actions, I'm just going to maximize the log probability of taking those actions again when I see those same states. Because I know that those are good actions that having taken them in the past, I was able to see positive rewards. And on the other hand, for this sequence of actions, which I eventually lost, I'm gonna think that these actions are bad because from these states I take these actions and they eventually led me to a -1 reward. So I'm gonna try to decrease the probability of taking these actions in the future. So in other words, I will maximize -1 times the log probability of taking those rewards, taking those actions from those states. So it is quite intuitive, right? And because we want to work in this reinforcement learning setting, again, we're going to incorporate this discounted rewards. So in other words, I'm going to discount rewards into the past. So at this point, if I see a reward of -1, then this immediate action that I just took, you will scale it by -1. But previous actions, I'm going to discount it by your gamma. So one of them will be -0.9, and then -0.81, and before that. So this will just very simply modify our objective function. Again, you're gonna try to optimize for your log probability of taking those actions given some states, but now the rewards are scaled either +1 or -1, scaled by your discount factors. So this presents a very simple algorithm, right? You're defining a policy pi that takes in states, goes through some parameters theta, and outputs your actions. And you initialize your policy network at random. So initially your parameters for your model are random. Now I'm going to repeat by taking a bunch of rollouts with respect to this policy. So using this policy, I'm going to sample a bunch of these actions and see what states I end up in and what rewards I eventually obtain. And we know that for some of these rollouts, you're going to get a good sequence of rewards with high rewards. And for some of these rollouts, you're going to get a bad sequence of actions that give you negative rewards. And given all these actions that I've taken, all these rewards that I've obtained, I'm just going to increase the probability of actions that have worked well with high reward. So maximize the log probabilities of all these actions with some discount factor. And for all of these that I've lost, I'm going to try to downplay the log probabilities of these actions by multiplying your objective by -1 and some discount factor. So this presents a very simple algorithm. Again, over here, you want to use an epsilon greedy method. So again, that's epsilon greedy from the lecture before, which is instead of just always following, taking action sample from your current policy, you want to also save a probability epsilon of exploring for random actions. And what are some benefits? So it does not require transition probabilities. So nowhere here have we actually derived our Q stars or V stars, our optimality equation that involve these transition probabilities and our expectations. And it predicts the policy directly. So this is actually a very simple algorithm. And you'll probably think, after all the trouble that we did, in deriving your Q stars and V stars from last lecture, it will actually be a surprise if this actually worked well, right? But in practice, it actually does. So, after training it for a bit, you can actually, so this is the opponent, this is you. It's very jumpy because at every time step, you're making a bunch of actions up and down. And you see, after training for a bit, it actually works really well. It's able to quite consistently beat the opponent. Yeah, you get a point. So then the question is, such a simple algorithm, why does this work? And if it really works so well, why did we go through all the trouble of deriving our value and policy iteration methods from Tuesday's lecture? And if it does work, under what scenarios does it work, and under what scenarios are there possible drawbacks to this method? So we're going to look at this method in more detail, and we're going to see, whether we can actually, give some guarantees for why such an objective function would actually work in reinforcement learning. So let's look at this. So I'm going to first start by defining a class of parameterized policies. So for each policy pi, it's associated with some set of weight parameters. So again, you can think of this as, if you're defining a neural network that takes in states, goes through some parameters data and outputs some actions, you will have this set of all your neural networks, each of them with one particular set of weight parameters. Some are obviously good, some are obviously, random and bad. So for each policy, I'm going to define its value. And what this value would be is, condition on this particular policy pi with parameters theta, the expected long-term reward by taking this policy in this environment. So again, this long-term reward would, take time steps from 0 all the way to your horizon. And for each time step, you observe a reward and you would discount it by gamma. So that's the value of each policy. And so according to this value, some values of theta, some set of parameters will give you a really good policy that consistently gives you really high expected reward over your long term. And some policies will give you very bad reward and just never really gets any reward. So we're also going to define two things. We're going to, again, revisit this in terms of trajectories. So trajectories are, starting from some state, taking actions, observing rewards, and going to next states. So I'm also going to write out the probability of each of these trajectories. So the probability of a trajectory is given by a couple of things. First of all, if you're in some start state, your policy, pi, with current value of your parameters theta, will define what probability of taking action A0 that your agent will currently take. And once you choose a probability of taking action A0, you would then have to give it to the environment and actually multiply it by the transition probability of going to your particular next state S1. And then once you're in S1, you're again going to reevaluate your policy with S1 as input and predict a probability of taking action A1. And likewise, given S1 and A1, you will multiply it by the transition probabilities that it goes to S2. So all this sequence of multiplications up until your horizon, that is equal to the probability of a particular trajectory. And likewise, I'm also going to define the reward of these trajectories, which is very simple. It just takes in all these rewards and sums them after multiplying by your discount factor to the power of t. So given these two things, I can write the reward for a particular policy with parameters theta as, instead of the expectation of the rewards under this policy, I can write it as the expectation under trajectories sampled by your probability distribution over all trajectories under your policy pi times the reward of each particular trajectory. So to see how these are equal, so obviously, inside the expectation, this, summation of rewards scaled by your discount factor is exactly your reward of a trajectory. And my expectations under a policy are exactly an expectation under the distribution of trajectories, because, for each trajectory, you're actually following your policy pi and taking actions as described by what my policy should be. So these two are exactly equal. So then the goal is, we can write the value of these policies. And the goal is to find the optimal policy theta star. And we know that the optimal policy would simply be an argmax over all values of your parameters, J of theta, which is the long-term expected reward under this policy. So this is a maximization problem. A general method to solve these maximization problems would definitely just be, taking a gradient and doing gradient ascent because you want to maximize. And you would take gradient with respect to your policy parameters theta. So how can we do this gradient ascent? So we know that the expected reward is equals to the expectation under trajectories sampled from the distribution of trajectories given by your current policy, the reward of your trajectories, right? I'm going to write that as an integral over trajectories, tau. And I'm going to try to differentiate this by taking the gradient with respect to J of theta, the gradient of theta with respect to J of theta. So I can move my gradient with respect to theta inside the integral because the reward of trajectories doesn't depend on theta. And if you recall, the probability of a trajectory is equals to the product of all of these terms. So, starting from initial state, looking at what actions your policy tells you to do, and all these transition probabilities. So taking gradient of this really, this huge bunch of multiplicative terms is intractable, right? You can't even think of how you can do the chain rule for this. So you can't really take a gradient of this with respect to theta. But there's some tricks we can do. So one trick we're going to do is that we're going to rewrite the gradient of your probability of trajectories with respect to theta. I'm going to multiply both the numerator and denominator by the probability of your trajectories, right? So these two cancel to be 1. So this doesn't really change anything. And then we also know that, the gradient of a term divided by the term itself is equals to the gradient of log of the term, right? This is just by calculus. So in other words, we've converted the gradient with respect to your probability of trajectories as, first of all, the probability of trajectory multiplied by the gradient with respect to log of your probability of your trajectories. So now putting this back inside, we're going to again get this integral over your trajectories, the reward of a single trajectory, and now this term, which is the gradient with respect to the log of the probabilities times the probability of the trajectory itself. And we know that this integral of tau, p of tau d tau, is exactly an expectation of the trajectories. Right? I can rewrite this as an expectation. And what's left inside the term of your expectation is the reward of your trajectories times the gradient of the log probabilities of your trajectories. So why is this more tractable? So let's see why in a minute. So again, we know that the probability of trajectories is equal to this really huge product of many terms given by your policy and your transitions. So we know that we are going to end up taking a gradient of the log of these probabilities. So you take log, the product becomes a sum, multiplication becomes log addition. You get this. And taking the gradient with respect to theta, one very nice property emerges, which is that the log probabilities of your transitions actually don't depend on theta. That's some unknown that's just given to us by the environment. So this term actually goes away. And all that's left is a summation over your time steps, the gradient with respect to theta, all the log probabilities of each of the actions taken at each time step as given by your policy. So we've now removed the dependence on your transition probabilities, which is really good for us because that was one big thing we had to deal with on Tuesday. And therefore, the gradient with respect to the reward of each policy is exactly equals to, it can exactly be approximated in this way. So replace this expectation with just samples. And for each of these sample, I'm going to sample some trajectories. I'm going to evaluate the reward of that trajectory. And I'm also going to compute the gradient with respect to each of the actions taken in that trajectory under my policy. So this gives us a very easy way of computing the gradient with respect to this reward, the gradient with respect to theta. Again, the benefits here are that all these terms are easy to compute, right? You can collect a bunch of trajectories from the environment under your current policy. I can evaluate the rewards of these trajectories. That's already given to me by the environment. That's just a sum of my long-term discounted rewards. And again, for each particular sequence of states and actions within this trajectory, I have a model that computes the probability of a particular action given that state. And the good thing is that we now no longer depend on these transition probabilities. So what is the interpretation of this gradient estimator? So it's very similar to the method of Pong that we looked at just now. If the reward of a trajectory, if R of tau is high, I'm going to push up the probabilities of all the actions seen that allowed me to obtain this trajectory. So that will be increasing, this will be high and positive. I'm going to increase the log probabilities of all the actions under this trajectory. And conversely, if the reward of my trajectory is low, so if this is high and negative, then I'm going to push down the log probabilities of all the actions seen under this trajectory. Which was exactly what we saw in Pong, right? We sampled a bunch of trajectories. We don't know what happened in the middle, but we obtain a reward at the end. So for all of these actions in the middle, so for all the summation over your t from 0 all the way to when you finished, I'm going to try to maximize the log probabilities with scale by positive reward, positive 1. And for these, I would kind of scale each of these by negative 1, so to decrease the probabilities of taking these actions that led to you losing. So these are actually the same. The intuitive algorithm that we derived for playing Pong is actually exactly the same as the gradient estimator that we saw was derived exactly. And that actually gives us a very nice algorithm. This is called the reinforced algorithm. It's also known as policy gradients. What you're going to do here is that you're going to start by initializing a differentiable policy pi of a given s with parameterized by some parameters theta. Again, you want it to be a differentiable so that you can actually take gradients with respect to theta to update your policy weights theta. And you're just going to forever repeat by generating an episode. Again, this episode, which is your sequence of states, actions, rewards, next states. This is exactly your trajectory. You try to sample these trajectories given your current value of the policy's pi. And for each step of the episode, I'm going to look at the cumulative return. And I'm just going to update my parameters using this update rule, which is the cumulative return times the gradients of the log probabilities of the action that you just took. And that will give me a rule to compute the gradients with respect to theta, and therefore update theta to get a better set of policy weights and a better policy. Again, when we say sample an episode or sample a trajectory according to your current policy, you want to do something that's epsilon greedy. So with 1 minus epsilon, follow the current version of your policy pi. And with epsilon probability, you would just want to sample randomly so that you explore the environment. And this epsilon should start really high. So at the start, when your policy is rubbish, you would just do all exploration. And slowly, as you get a better policy, you will also follow your policy more rather than exploring. So this seems a very simplistic method, right? I think the main issue here is that was saying that this trajectory can occur over a very long term, maybe 1,000 time steps before you actually observe a reward. So it's very simplistic to say that if this whole trajectory over 1,000 time steps ends up being good, then all of the 1,000 actions were good. So that doesn't seem ideal, right? It seems like if you did a sequence of 1,000 actions, maybe some of them were bad and only some of them were good, that actually led to a high positive reward. Although it's simplistic by an expectation and we do enough samples, it actually averages out and it actually gives you a very good, decent estimator to get a good policy. But again, that requires many samples, right? So again, if you looked at the slide we saw previously, all your learning your Q stars and your V stars and all the methods we saw on Tuesday's lecture, they are much more sample efficient. On all these policy gradients, if they actually work, they're more sample inefficient and requires more samples. And requiring more samples also means that if you have very few samples, you're going to suffer from high variance. So how can we actually do better?